Welcome to the presentation about my dissertation called From Valid Measurements to Valid Mini-Apps. My name is Jan Patrick, or JP Lair, and I'm very happy that you all join me for this presentation. I want to specifically thank all the committee members for actually taking the time, reviewing my thesis, and joining for this presentation. Now let us first set the scene and where my dissertation is actually located. And we think about performance engineering, and performance engineering, which is actually carried out throughout the life cycle of a target application, is somewhat of a cyclic approach, of a structured approach to investigate and improve potentially the performance of an application. So we start out with a target application and we perform performance measurements that generate data. This data is then turned into insight during performance analysis. And that insight is then used, for example, going the upward arc for performance tuning, where you would actually improve the performance of the application, or potentially you want to do performance exploration, for example, trying out new programming models. Now, through all these stages, some recurring tasks and challenges exist. So for example, during the performance measurement, you want to determine and minimize the impact of measurement on the recorded data. In performance analysis, you want to identify important regions and determine limiting factors. For performance tuning, you actually want to remedy these limiting factors and improve the application performance. And for performance exploration, for example, you want to create a mini app for easier exploration of, as I said, a new programming model. And now if we set the contributions of my thesis into perspective of these four stages, first, the thesis does not contribute to performance tuning. However, it does contribute to performance measurement, where we investigate the influence of different performance analysis, different performance measurement tools in chapter 3. Oh, danke. So sorry for the, I hope now that the camera scene is actually working. Yeah, okay. And so in chapter 3, we investigated the influence of different performance measurement programs onto the target application in more detail. These insights that we get there led to the development of PIRA, which is the performance instrumentation refinement automation that was presented in chapter 5 in my thesis. While we were working on PIRA, we realized that we need a suitable abstraction, which led to the development of MetaCG, which is sort of an infrastructure for program analysis. And then finally, we occupied ourselves looking at a tool-supported kernel and mini-app abstraction approach that is presented in chapter 6 in my thesis. The first chapter generally introduces the topic, and chapter 2 gives some background information about the different techniques. So let's start, and today we will mostly look at PIRA and MetaCG, and I list the different venues where I published about the different works. But let's first look into the influence of measurement and motivate PIRA. So when we look at the overhead, the application slowdown that is on the y-axis here, meaning 1.0 meaning no slowdown compared to the vanilla application, whereas 2.5 meaning the application runs 2.5 times slower than the vanilla application, we actually see that the automatic score P instrumentation has a large runtime overhead in 10 out of 14 cases. Now score P offers a filtering mechanism which filters inline functions from the measurement, and if we apply this, we actually can reduce 2 of the perturbations here down to acceptable levels, and so we still have large runtime overhead in 8 out of 14 cases. The second challenge that performance analysts face is the granularity of the measurement. So again, automatic score P instrumentation actually measures many irrelevant functions in the profile, and that's actually the reason for these slowdowns. So here, for example, this is a screenshot of a profile, and we see that only 2 functions from all these entries are actually meaningful for any analysis. And that goes on if we go down that profile. So we see just many functions not contributing enough runtime to the actual measurement. So the challenge is that we have significant runtime overhead with automatic compiler instrumentation because and we have too many irrelevant functions in the profile without filtering. So what we want to do is we want to reduce the runtime overhead for practicality, and we want to limit the functions to only relevant ones. And this is actually currently performed manually during performance analysis. So our goal then was to automatically eliminate irrelevant functions from the measurement to present only relevant ones to the analyst. And we do this by first performing a whole program analysis to heuristically identify promising regions to place measurement probes, and second, to refine the probe placement iteratively and using profiling, feedback, and source code information. And if we relate that to the two tools I'm going to talk about, then MetaCG correlates more to the whole program analysis part, and PIRA more to the iterative refinement, although we're going to see that these are tightly integrated. Let's start with MetaCG. MetaCG provides an annotatable call graph or CG library independent of the compiler. It allows the annotation with user-defined metadata per function, and for example, we have the number of statements here that we're going to see be used in PIRA later on. We also have variable and type statistics. It moreover provides an import and export functionality for the CG such that we can reuse it across tools. When we look at the construction that MetaCG actually implements, we see that CG Collector first generates partial call graphs per translation unit using the Clang Abstract Syntax Tree, or AST. These partial call graphs are then merged into the resulting whole program call graph, which I'm going to refer to as the MetaCG throughout the remainder of this presentation. Now, during this merge step, the user-defined metadata is actually handled explicitly with user-provided implementations on how they are merged. Finally, and this step is optional, you can validate the statically constructed call graph against a call graph that was recorded from score P during a run. So this is an input-sensitive call graph. When we evaluated the MetaCG approach, we actually had two scenarios in mind. The first one is the actual CG construction, in which we construct the CG for a target application and then use CG validate to count and see which edges are missing. The second part is we want to see about the positive impact of MetaCG in a different tool, and here we use typeart. Now, typeart is a memory tracking sanitizer that relies on instrumentation, and it implements a filtering mechanism to reduce the runtime and memory overhead. What it does is it instruments memory allocations that are relevant to a particular API. So for example, if you want to do type analysis for MPI calls. However, the default filter is limited to one translation unit at a time. We then applied the approach to different target applications. The first one being the well-known Lulesh mini app with roughly 5,500 lines of code. It is a C++ MPI parallel mini app computing shock hydrodynamics. The second target application is AD Lulesh, which is Lulesh with added algorithmic differentiation using Codipack, which was created by my colleague Alexander Hück. Then we have the EOS MBPT simulation, which is a C++ and in our case sequential astrophysics simulation developed by Dr. Christian Drischler from LBNL. And finally, we have the ice sheet and sea level system model, or ISSM for short, that is a C++ MPI parallel ice sheet simulation. So let's look at the CG construction first. When we looked at the missing edges and compare them to the number of edges we're actually checking, we see that we do miss edges in the call graph. And we see that this is roughly between 5 and 10% of the overall edge count that we're checking. However, missing edges alone don't tell you too much. So we looked at whether we're actually missing also function nodes, what we find out we did, and we see that specifically in ISSM we have a somewhat large number of function nodes we're missing, and I'm going to talk about that. And we then looked at the number of functions reachable from main and how that changes if we patch in these missing edges that we identified. And here we can see that specifically for AD Lulesh and ISSM, the numbers are somewhat large. However, in all cases except ISSM, this was not an impediment to the actual workings of PIRA, but for ISSM it was. And this is actually due to ISSM using function pointers for setting the solver. And these function pointers are specifically the problem here because they reach across different translation units, which is currently not that well supported in MetaCG, and we're working on that. For the AD Lulesh case, and this applies to the missing functions in general, apparently some calls to certain templated constructs are not present in the Clang AST, which was somewhat surprising to us. And again, it's an issue we're currently looking at and we want to address. Also, please note that currently MetaCG assumes the main function to be the starting point of the call graph, and so we're not seeing static initializers as part of the actual call graph. That may change in the next version of MetaCG. Now, looking at the other part of the evaluation, when we added whole program analysis reachability analysis support in type art using MetaCG, we were interested in the reduction in tracked allocations that we were able to achieve with that. And we did that again with Lulesh and AD Lulesh. Now for Lulesh, the numbers are not that impressive. However, if we look at the AD Lulesh case, we see that we can reduce the number of tracked stack allocations to only 72 in the CG filtering approach compared to 615 in the regular filtering approach. And that translates to roughly 14,000 stack allocations being tracked when we use the CG filter, compared to over 32 million allocations being tracked when using the regular filter. And that is a reduction by a actual multiple numbers of magnitude. And we actually seen runtime improvement. And this, so we can reduce the runtime overhead by roughly 6%, which is quite significant if you think of large-scale parallel applications. So in summary, MetaCG offers a lightweight whole program call graph representation that can be freely annotated with user information and serialized into JSON. The construction is done on a per translation unit basis on the Clang AST and the subsequent merge step. It can be integrated into tools for whole program analysis, as we have just seen with the type art example. And now I'm going to present how PIRA actually uses the meta information that we attach into the MetaCG for low overhead performance profiles. So let's look at PIRA. As a reminder, the goal of PIRA is to automatically refine performance profile measurements to only relevant parts of the application. So basically, turning such a profile into such a profile. And we do that by a filter and expand approach, where we remove functions based on their runtime behavior, and we add functions heuristically based on source code features. From a high-level point of view, PIRA gets as the input a target application, its MetaCG, and a PIRA configuration. It then performs first an initial PIRA instrumentation configuration, of short IC, and that is always determined statically purely using the MetaCG information. Now, having this IC, it then compiles the target application during the build step to get the instrumented binary, then executes the target application during the run step to get the Scorpy profiles, and then analyzes the MetaCG and the profile to determine the next IC using heuristics. And these heuristics are the refinement iterations that use static and dynamic information. This is what we call the build, run, analyze cycle. Now, looking at the software architecture from PIRA, we opted for a loosely coupled component-based design where we have the orchestration layer sitting on top that actually controls the invocation of and the data movement between the components, and the implementation actually tightly follows the build, run, analyze cycle. PIRA comes with its own LLVM plugin that actually inserts the function instrumentation before the optimization stage, and it relies at the measurement layer on the Scorpy measurement infrastructure that records the runtime information at when the target application executes, and we use the cube library to access that profile information again in the analysis component, where PIRA provides the profile-guided instrumentation selection, or PGIS, that actually implements the different selection heuristics. So I'm going to focus on the PGIS tool because that's the most interesting part, and I have put down extra P here, which is not a tool that I developed, but the group of Felix Wolf that allows to construct empirical performance models that PGIS can use in one of its heuristics. Speaking of which, we currently have 4 heuristics implemented, which is first the statistical statement aggregation that is used for the initial instrumentation, and pretty much when we apply the expansion and an iterative descent. We then have the runtime or hotspot heuristics, which identify runtime hotspots based on raw runtime measurements. Similar, we have the performance model heuristics, which identifies runtime and scalability hotspots based on the aforementioned empirically constructed performance models by extra P. The most recent addition is the load imbalance detection, which identifies load imbalances, meaning uneven distribution of work in parallel programs. And I'm going to present the 3 still black marked heuristics here, and I'm not going to cover the performance model heuristics because how it works is very similar to the runtime or hotspot heuristics, but instead of comparing the raw runtime, it first evaluates the performance model and compares the resulting values. So let's start with the statistical statement aggregation heuristics. This participates in pretty much all of the static selection decisions in PIRA. It uses the aggregated number of statements. And let's look at an example how this works. So assume we have a MetaCG that is similar to the one in A, where the nodes are the functions, the edges are the call edges, and the labels here denote the individual statement count per function. We first sum up the statements were rooted at a particular node, which gives us the particular statement count here. And then, and this is an approach that was actually presented by Iwański and Bischoff in 2016. What we do as an extension to that is we then compute the threshold that we use for filtering based on the distribution of these number of statements in the graph. So here we are computing the median, for example, and that results to the number 47. We use it as a threshold, and we prune everything where the aggregated number of statements does not cross that threshold. Now in PIRA, we actually use what we call the unique median, but I don't want to go into too much detail here. For the runtime or hotspot heuristics, we filter using the inclusive runtime, and we also expand using the aggregated statements that I showed before. Now please note that this is the first refinement heuristics, so this has actually static and dynamic information attached. And it effectively filters small and short-running functions from the measurement. So let's go through the example. We first decorate the MetaCG with the profile information that is indicated with the inner white circles saying that here is runtime attached. We're then processing the node that's currently pointed to by the arrow. We then compare the runtimes of its children, and we see here, for example, that the runtime of A is larger than the runtime of B. So we set A as the principal node, which is then going to be processed further. When we then process A, we realize that for its child nodes, no runtime information is currently available. So we switched over to the static instrumentation expansion. In this step, we then use again the aggregated number of statements and now compute the threshold localized to this particular node. So in this example, the threshold is computed as the value 3. And if we apply that threshold, we're filtering out the smallest function here, leaving the circles, the nodes marked with the black circles around as the final IC. Now looking at the load imbalance heuristics, load imbalance detection heuristics, or LIDE for short, I want to first recall what a load imbalance looks like. So here we have two processes, P1 and P2, that compute some functions. And we actually see that for the function f tilde, both processes take different amounts of time. So this is what basically is a load imbalance. However, to the outside, it may actually seem as balanced because we have a synchronization point at the end. And so P1 needs to wait longer for P2 because P2 actually needs more time to compute f tilde. How we detect such load imbalances is that we evaluate the load imbalance percentage across the processors. And what we basically do is we compare the maximum time that is used to compute the function compared to the average time that is needed to compute the function. And we normalize that to the 0-1 interval. This excludes balanced and short-running functions. And so we're left with longer and actually imbalanced functions, which is the target of the heuristics. Let's look at this through an example. So here we start with a MetaCG that looks like this, and again we already have the aggregated statement count attached to the nodes. We then first do the initial instrumentation from the root node and the first level of children. Now then we compile the target application using this IC to generate profile measurements. As a first step then in the refinement, we do the runtime threshold filtering. So here we simply exclude functions that do not cross a certain runtime threshold in order to eliminate irrelevant functions. In the next step, we then actually evaluate the imbalance percentage. And now let's assume, and I'm sorry, I forgot to actually use the pointer here. Let's assume that the node here does evaluate to a balanced node. So we look at its children and do a static evaluation, see whether from a static point of view this function has enough number of statements to be considered relevant. With this low number 4 being in the node, we would consider it irrelevant and we would also exclude it from measurement. This means that we would completely ignore this whole subtree for any subsequent measurement. Now in the example, the function here with the 17 as a label also evaluates as balanced. However, the child node with the number 10 is actually large enough to be considered for the iterative descent, meaning that for the next iteration we actually descend into this node, marking is for instrumentation, and having this IC then being used for the compilation. So now the steps C to E are iterated. So we do the runtime threshold filtering, we do the load imbalance evaluation, and then we do the iterative descent in an iteration. Now let's assume that this node actually is imbalanced. We would then notify the analyst that a load imbalance has been found, and we would do what we call context handling, in which we would instrument all paths to the main function upwards in order to give an analyst more insight in which context this function was actually load imbalanced. When we looked at the evaluation, we actually had three criteria we wanted to see. So the first one is the successful refinement towards points of interest. Then second one is the runtime overhead. And the third one is the number of recorded functions. Our evaluation setup is we use the Lichtenberg 2 cluster and the software versions using Clang 10, Scorpy 6, PIRA 034, and MetaCG 026. So first, let's look at the runtime heuristics. In this example, we use a very aggressive inclusive runtime threshold filtering, meaning that we want functions to consume at least 50% of the overall program runtime, or the overall time that main and all its child node take. And we run 4 PIRA iterations. In general, we see that we maintain a quite low relative overhead here, being close to nothing. I want to point out that in the case for H264 ref, for example, the static selection actually introduces quite a number of, quite percentage of runtime overhead. However, using the refinement with the runtime threshold filtering reduces this again to almost no overhead in the first PIRA refinement iteration. We then also, and this leaves us with a good overview measurement in 8 out of 14 cases. Good overview measurement meaning low overhead and the runtime being attributed not only to the main function or to like 1 or 2 functions, but actually giving you an overview of the application. And we validated that with looking into the applications using vTune. Looking at the number of actual regions or functions we instrument, I want to highlight particular 3 cases where we can reduce the number of functions relevant to the overall execution time quite drastically. So specifically in the case of 447 DL2, we can reduce the number from 115,000, which is present in the not filtered Scorpy profile, to just 17, and the actually filtered Scorpy profile being reduced to number 4,000 functions. Now please note that the number 17 is different than the one in the table in my dissertation. However, in the dissertation, it seems that there's an error. I rechecked that with which actual measurements I did, and the number 17 seems to be the correct one. Now looking at the evaluation of the load imbalance heuristics, we apply that to 2 different scenarios. The first one is the Lulesh application. Lulesh allows to introduce artificial load imbalance using a parameter B that determines the amount of additional work that is introduced. It does that by changing the time required to compute the equation of state for the material properties during the simulation. The other one is the ice sheet and sea level system model, or ISSM, and we are simulating a Greenland's ice sheet. As a comparison, we have a manual performance analysis of ISSM that was carried out by my colleague Yannick Fischler. So when we look at the numbers here, we see that for Lulesh, first of all, for increasing Bs, meaning increasing artificially introduced load imbalance, the load imbalance percentage also increases, meaning that the metric actually does what it's supposed to do. And for ISSM, we tested 3 different setups where we have 2 different model sizes. Here, G4000 being the smallest model with running 1 solver iteration. So then the smallest model with running 10 solver iterations, and a larger model with running 1 solver iteration again. And we see that the load imbalance percentage actually decreases when we increase the actual runtime of the solver. This is due because the load imbalance actually comes from the creation of the system matrix. And these experiments were run with 64 MPI processes. Looking at the runtime overhead that our method introduces per instrumentation, we actually see that for Lulesh we're generating negative runtime overhead, which was quite surprising to us, and we still have to look into a little more why that is. Particularly compared to the Scorpy full instrumentation, that's a dramatic reduction. seeing that score P actually introduces 10 to the power of 4% of runtime overhead. And even if you employ the inline filtering, score P still introduces about 80% runtime overhead. Looking at ISSM, PIRA actually generates some overhead with the smallest model and 96 MPI processes. However, we see that this overhead increases with the number of MPI processes, and so we would assume that this is actually static setup overhead. However, for most of the measurements, we're actually below 15% of runtime overhead, with this one actually being the sole exception. If we compare that to the regular score P profiles that you would do, even if you apply the inline filtering, you still get roughly about 500% of runtime overhead, meaning that it's somewhat impractical for performance analysis. And so again, also here we have quite a significant improvement. So in summary, PIRA automatically refines score P profiles to relevant regions, which reduces the runtime overhead and limits the number of functions to inspect by an analyst. It relies on the whole program call graph representation MetaCG to do so. It implements different heuristics for measurement refinement. And the introduced runtime overhead typically stays within 5% for the hotspot heuristic and 15% for the load and balance heuristic. Finally, I would like to highlight some of the work we did for the tool-supported kernel extraction. Now, in the mini-apex approach and workflow, we want to extract tool-supported kernels and mini-apps from existing applications. And we came up with a 4-stage approach to that. So in the first stage, we do kernel identification, and we employ PIRA for this automatic kernel identification. For the second step, we actually implemented a Clang-based source-to-source tool using MetaCG to determine the relations between the functions in the code base. Then, in the third stage, we capture application-level data using a newly created type-safe checkpoint restart API that is based on typeart. So, looking at this API a little more, we can actually see that the application, when compiled with typeart, uses these callbacks to keep track of the allocations in the program stored within the typeart runtime library. Then, the checkpoints that we insert when executed, actually query this runtime to obtain information about the address and the type and the size of the memory region that's going to be checkpointed. If that succeeds, then the runtime dispatches the checkpoint to the actual backends, and we support the 2 MPI parallel libraries, FTI and Veloce. Finally, we do a validation of the execution similarity using a hierarchical clustering approach. And for that, we obtain the execution characteristics, meaning we record hardware performance counters and the dynamic instruction mix of the execution of the application. And then this is fed into the hierarchical clustering of regions. Now, we applied this approach to the EOS MBPT app that we saw before with roughly 8.5 million lines of code. And the goal is that we create a mini app that is suitable for parallelization using the DiscoPop tool. DiscoPop is another tool developed in the group of Felix Wolf that suggests parallelization opportunities. Now, PIRA identifies 3 kernels in total that consume roughly 99% of the overall runtime. And in the table, we see that the lower 3 functions are actually the kernels that are identified, and the upper 2 are actually on the call path to these kernels. When we applied the Clang-based source-to-source translator and created the mini-app, we then actually manually added the source code of the Monte Carlo library used in the simulation to expose more potential parallelism to the DiscoPop tool. However, still with this manual addition, we can see that we reduced the number, the lines of code by a factor of over 7,000, the number of functions by almost 400x. And we also reduced the number of reachable functions and the variables and the types by also some more factors. Now, looking at the execution similarity between the between the original application and the mini app, we actually see that for most of the instruction categories that are captured, it's quite the same. Only when these darker colored bars actually exist, we see a difference between them. And here, the largest difference is in syscalls and system calls, which we believe that the is due to the original application actually performing much more file I/O than the mini app. So in conclusion, we can say that whole program analysis efficiently reduces measurement overhead for instrumentation-based performance measurements. PIRA implements different heuristics for different analysis scenarios, and MetaCG offers a lightweight representation that allows the integration into existing toolchains for whole program analysis. The tool-supported mini-app extraction can simplify the creation of representative mini-apps to enable and assist in performance exploration. As future work for MetaCG, we plan to improve the precision of the CG construction, in particular with respect to the function pointers, and we envision a benchmark suite for call graph construction tools and algorithms. For PIRA, we want to look into combined heuristics to reduce the number of experiments actually required by an analyst, and we think about paradigm and library-specific heuristics, for example, with respect to OpenMP or the PETSI library. The mini-Apex approach, we want to apply that to more use cases and particularly to parallel target applications. While we do that, we think that we need to do improvements to the source-to-source translator, for example, to better handle multiple translation units and aliasing. And with that, I come to the summary of my talk. So, automatic compiler instrumentation results in significant measurement overhead. Our tool PIRA automatically reduces the measurement overhead with heuristics for hotspot detection, scalability study, and load and balance detection, which typically produce less than 20% runtime overhead. Our library MetaCG offers a lightweight whole program call graph representation that is reusable across tools. And finally, our mini-Apex workflow allows to construct representative mini-apps, as we have seen with the example where we reduced an 8.5 million lines of code physics simulation to roughly 1100 lines of code mini-app. The tools that I've talked about are available on GitHub under BSD 3 clause license. And with that, I thank you very much for your attention, and I'm happy to take questions.